Good morning, everyone. My name is Dikaen, and today we are presenting our computer hardware diagnosis system. Our team, Group 3, consists of Wong Man Yi, Lim Jiahui, Dikaen, and Chi Fang Yi. For the introduction, in both personal and business environment, we rely heavily on computers, where even minor technical issue can lead to major disruption. We developed this system to help users troubleshoot common hardware and software problems efficiently, even without advanced technical skill. Our goal is to reduce both troubleshooting time and repair costs. The primary challenge is that diagnosing issues like power failure or overheating requires specific expertise that many users lack. However, because hardware troubleshooting follow repetitive pattern-based process, it is the perfect candidate for a knowledge-based system. By automating this expert logic, we provide accurate decision support and reduce the heavy dependency on human technician. We have three main objectives for this project. First, to develop the expert system using the Philips programming language. Second, to translate expert knowledge into facts and if-then rules to ensure consistent decision making. And finally, to provide a platform where users can identify root hardware faults simply by entering their computer symptoms.
Fang Yi. Now I'm going to explain data collection and facts. The knowledge used in this system was collected primarily through an interview with an experienced computer hardware technician. The secondary knowledge source we use is domain knowledge from validated computer maintenance practice, which are used to support the expert's insights. Based on the data collected, the key symptoms and facts used in the system include power and LED status, operating system booting, display and hard disk activity, physical signs, some performance issues, and power management. And for the logical representation we use is if-then rules, which are used to infer specific hardware faults from user-provided symptoms. Next, for methodology, among the kind of knowledge acquisition, the method we use is structured interview. Firstly, we plan our interview. After that, we conduct the interview with a computer hardware expert. Next, we summarize and extract knowledge into if-then rules. Lastly, we implement our knowledge into CLIP's programming language. This is the tree-based diagram we used to represent reasoning flow. So basically, the system will ask a few computer performance related questions, and based on the user's answers, the system will find out whether there is any issues with user's computer hardware. If yes, system will come up with a diagnosis result, and if there is no problem with user's computer, then system will output no major issues detected.
Hi, my name is Wong Man Yi. Now I will demonstrate our computer hardware diagnosis system, which is a rules-based knowledge-based system developed using Philips. The system works by asking the user a series of yes or no questions, converting the answer into facts, and using forward chaining to infer a hardware problem and provide a recommendation. In terms of implementation, the system defines several templates such as person, symptom, and diagnosis. These templates are used to store user information, system facts, and the final diagnosis result. The system also uses a function called ask user to standardize user input. This function prompts the user with a yes or no question, convert the input to lowercase, and return a consistent value so that rules can evaluate condition correctly. Next, each diagnosis step is implemented using if-then rules. For example, in the check power issue, if the computer cannot turn on and the power LED is off, the system infers a power supply value and asserts a diagnosis with a recommendation. We also develop another rules such as startup, check boot issue, check display issue, check heat issue, check battery issue, check network issue, check noise issue. So total our rules have 9 rules. Now I will start the system demonstration. Like run the program. Reset. Run. First, the system displays the title and asks the user to enter their name. The name is stored as a person fact and the system greets the user before starting the diagnosis process. The system starts by checking whether the computer can power on. Based on the user response, it determines whether the issue is related to power or hardware components. Next, the system checks whether the computer can boot into the operating system. This allows the system to identify possible hard disk or operating system issue. The system then checks for display problem. By asking about the monitor display and HDD activity, it distinguishes between VGA cable issue and graphic card issue. After that, the system continues with overheating, battery, and network check. Each phase narrows down the possible cause by accepting new facts and triggering specific rules. Finally, the system checks for unusual clicking sound, which may indicate a failing hard disk. Once a root is satisfied, the system asserts a diagnosis fact. The system then displays a diagnosis report showing the detected problem and the recommended solution for the user. This concludes the system demonstration. Thank you. Now I will pass to Jiahui to present the another part.
First, let's discuss the technical construction. We combine 4 key clip functionalities. We use template to structure data and assert facts, specifically check phase to control which diagnostic stage is active. We develop rules using nested logic. This allows the system to ask deeper questions like checking hardware edge only when necessary. We also implement pattern matching. This is ensure the system only fire rules for current phase, keeping the flow organized. And finally, we use variables to dynamically store user input and verify identity. Moving to our results. This test case we use TAMI, demonstrate the core strength of our system, forward chaining combined with phase control. Notice that when TAMI confirmed the PC could turn on and boot, the inference engine intelligently skipped the power and motherboard check. The critical moment happened when she reported no display, but confirmed the HDD LED was blinking. The system successfully matched this symptom to rule 4, inferring that the PC was processing data but failing to transmit video. This led to an accurate diagnosis of a VGA cable issue, proving our logic correctly isolated the fault. In conclusion, we have successfully met our project objective. Our system major strength is the phase control logic. By dynamically asserting and retracting facts, we ensure the diagnosis is fast and never gets stuck. However, we acknowledge a limitation by the system currently runs a command line interface which is not user-friendly. For future improvement, maybe we plan to integrate a GUI. That's all from us. Thank you.